Next up, I invite Mr. Ajit Dhumale to deliver his talk titled Protecting Containers and the Ship Throughout Their Journey. Ajit Dhumale is a software security enthusiast with over 25 years of experience in software product development. Ajit holds a BE degree in computer science from Mumbai University and works on cloud workload protection products at CrowdStrike. Previously, he led a black box web application security scanner and signature development team. He holds multiple patents in the data protection area. He also has been a chapter co-leader and an active speaker at the OWASP Pune chapter. Welcome, Mr. Ajit. We're pleased to have you with us. Over to you.
Hey, thank you. Thank you very much. So just want to check if you guys are able to hear me.
Yes, you are audible.
Okay, thank you. So let me start by sharing my screen. Okay, good morning. Welcome, everybody. So today we are going to talk about protecting modern applications. So we're going to talk about pre-production security for modern applications and post-production security. Yesterday, Ramesh from CrowdStrike covered modern application stack in his talk. So modern applications are built as microservices. They are packaged in form of containers, and they're deployed on clusters, which could be in public cloud, private cloud, could be on-prem. And these are orchestrated using orchestrators like Kubernetes. Right? So, and we are going to cover some of it, just a recap of some of the talk that Ramesh did in yesterday. Okay, so I'm sure this slide you must have seen in yesterday's talks. This is about application development and deployment lifecycle, nowadays called as DevSecOps. So in pre-production stage, you write your code, build it, test it, and then release it. In that concludes the pre-production steps. Then in post-production, you take the deployed release applications and deploy them, then operate them, where you scale them, you handle failures and scaling, and then you keep on monitoring the applications for their health. Okay, so let's actually directly jump into pre-production security. Okay, and let's take an example from something outside the applications and softwares, and let's talk about a cookie factory. So what happens in a cookie factory? Right? So you start with ingredients. You take flour, sugar, butter, and then you mix those ingredients. You bake them. Once the cookies are ready, you will do the quality check to make sure that the cookies have turned out fine, and then you will package the cookies in nice boxes, and then you will basically store them in warehouses, and later on those will be delivered to your customers from the warehouses, right? So now suppose we are running this premium cookie factory. We are very famous. We have a lot of loyal customers. We are doing billion-dollar business. What would we be worried about from the security side of this, right? So we make sure each and every cookie that we deliver to our customers are hygienic, safe, pure. What are the risks? So risks here are that because of our negligence or oversight, it may happen that we may ship bad cookies. The other possibility is that our competitors and adversaries might try to basically tamper with our cookies in some way so that they can basically try to damage our brand reputation. So we have to guard against all of this. So what would we be looking for? So at the initial stage, when we are looking at ingredients, we will first make sure that we are sourcing our ingredients from trusted sources. Then we will make sure that inspect them and make sure that they're pure, safe, and hygienic. Once we do that, then we will go and start mixing and baking them. But at this stage, what are the risks? What if our competitors sneak into our factories and tamper with our mixing units, our ovens, and try to inject something malicious or something dangerous in our cookies, right? So we have to guard against that. So we have to make sure that our supply chain pipeline, which is our mixers and ovens, are tamper-proof. Nobody can basically mess with them. Now, once the cookies are ready, we'll definitely like to make sure that the cookies are safe. So we'll inspect them. We will test them to make sure that they are safe for consumption, good enough for our customers. Once that is done, we will pack the cookies and we'll make sure that our packing is tamper-proof so that later on, nobody can insert something into those boxes. Then we will take those boxes and store safely in our warehouse, right? So in our warehouse, we want to make sure that the boxes, basically, only our boxes will be shipped to our customer, not some fake boxes or somebody else's. We don't want them to be able to sneak in counterfeit boxes, right? So now this is about cookie factory. But how does this apply to software? How does this apply to applications? Let's see if we can see some analogy or some connection when we come to applications. Right? So now let's look at application lifecycle, and we will surprisingly see a lot of commonality between what we saw in our cookie factory. So here we see that we start with design and code, and our ingredients here are our code as well as the third-party library that we are going to use in our software. So if it's a Java JSP application, then our code would be JSP scripts, and the third-party libraries or dependencies, as we call, would be Tomcat web server on which we are going to run, say, logging-related libraries, caching-related libraries, all that. Those are all our ingredients. So it's our code and third-party libraries that we are going to use. We take those, we mix them at the build stage, we bake our application. Once the application is ready, baked, we will test it. And once it is tested, we will, just hold on, give me 1 second. We will release it. And modern applications will be released in form of containers, and those will go and sit in our image registry. Surprisingly, similar stages like cookie factory, right? So now here, if we have to worry about security, because we want to make sure that each and every piece of software that we are developing and we are running in our production clusters are safe and secure, we have to worry about exactly same things that we talked about in cookie factory. So we will start with ingredients. So once again, ingredients here are our application code and scripts and the third-party libraries. So for our custom software, we will use SAST, which is called as code scanning. So we'll, after writing code, we will scan our code to see if there are any security issues. And for the third-party libraries that we are going to incorporate in our software, we will use SCA, which is software composition analysis, which will basically check which third-party softwares we are using, what is the version, and is there is known security issue with that particular version of the library. Just to basically give an example, a very recent one, I'm sure most of you heard about this remote code execution vulnerability in Log4j. It was called Log4Shell. So if you're using, say, a logging library of Log4Shell in your project, then SCA is the one which will basically tell you which version of Log4j you're using and is it vulnerable, right? Because at this stage, you can basically say, okay, if I'm using some vulnerable library, I'll look for other alternative, or I will use a newer version where the vulnerability is fixed. Once that is done, we need to basically look at security of the build stage. So build stage is where your software is getting mixed and baked together. So these would be your CI/CD pipeline, your Jenkins, Bamboo stages. here you need to worry about they being tampered. So we need to basically make sure that they are tamper proof, so that when your source code and third-party libraries are getting built, mixed together, nobody is able to sneak in some malware or crypto miner into your artifacts when they're getting bundled in form of a container. Then once your basically application is ready, you will like to test it. And the testing here, apart from functionality testing, you will also perform security testing. And that's called DAST, which is dynamic application security testing, which is also called as pen testing. You could do automated as well as manual pen testing of your application. Once you're satisfied with that, you would release your application in form of a container. You will make sure that you are packing your container and signing it so that it is tamper proof. Nobody can sneak in something malicious into your container later on. And once the container is ready, you would like to scan the final product, like the image, for security. And you can do static analysis on the image, static security analysis. As well, you can perform dynamic security analysis. Okay, so let's look a little bit deeper into image security. So containers, basically with microservices-based architectures, the application being packaged as containers provides a lot of advantages. So one advantage is a container image is a self-contained packaging, and it is portable. What is meant by it is portable? What it means is that the container, because it has everything that it needs embedded within itself, you can execute that container on your dev environment, on your, in fact, dev machine, or even on your laptop, or in a staging environment, or production, which could be private cloud, public cloud, or on-prem cloud, and the container will behave exactly the same. This actually is very important from portability and deployment point of view, but this also basically helps us doing security analysis on our applications. Because once a container image is ready and it is self-contained, it is going to behave exactly the same in all environments. We can actually inspect it for security. And once we say, okay, I inspected image for security, I can basically be rest assured that the same security would basically be applicable in all the environments. So what is an image? What is a container image? So container image consists of a file system bundle, which includes your application binaries and scripts, and all the dependencies that are needed for your application. So it should be third-party open source libraries, any tools that your application needs, any utilities, as well as system packages like, say, for SSL encryption or network HTTP processing. All that is bundled in form of a file system bundle, which is, you can say, is very, very similar to a zip file or a tar file, right? Along with that, there is some configuration. So configuration typically would include under what user ID this container is going to run when we run this in production, or any environment for that matter. And what would be the starting point? What would be the first process that would run when this container starts? All this is there in the container image. Now let's look at security aspects of it. First is, it's always a recommended practice to harden your images. So what is mean by hardening images? It's very similar to OS hardening, right? In OS hardening, what do? You basically make sure that you're not including any component or library which is not needed, right? What do we achieve by doing that? This helps us basically make sure that we are not we are restricting the attack surface. So if we are not including certain library in our container, it means that it cannot be exploited. Right? So suppose you were writing an application which doesn't need any logging. There is no reason why we should have, say, for example, log4j in that container, right? If there is no log4j in that container, chances of it getting exploited doesn't exist. So remove all the unnecessary packages and utilities from your image. That would basically leave lesser opportunities for the attackers to attack. Images are built using layers. So it's not that for each application, each container, you start from the scratch and install all the dependencies and then application. You would basically, for example, if you are producing a lot of Java-based web applications, then many of those applications will have common layers like the common web server, Apache Tomcat, and certain common libraries. And the application could be specific. So in this case, you could take Apache Tomcat as a base container, and that's a base layer for all of these containers, and you would install custom applications. So when you're taking base images, make sure that you're taking them from trusted sources, and you are basically taking lean and mean base layer, which also doesn't include any unnecessary dependencies in there. Once you have built your hardened image, you can perform static scanning on it. So the various things that you can look for, one is software composition analysis. We talked about it just a few minutes back. So you can check all the dependencies. So software composition analysis would scan the image, inspect it, and give you a list of what is called as bill of material or a software inventory. It will list all the packages, tools, and libraries which are there in that image and which version they are. And then you can map that to, okay, this software, this version, is there any known vulnerability? So known vulnerabilities are typically the popular form of them is CVEs. So you can check, okay, does my image suffer from any of those CVEs? If there are any known vulnerabilities and CVEs, then you can basically analyze them, and you may go back and replace those libraries with the safe version. You would also like to basically check if somehow some malware crypto miners have got sneaked into my image. They could come from base image because somehow you took a base image, even if it was trusted source. If the source somehow was compromised and some of the malware got introduced in the base layer, or it could be that in your engineering process and development process, without knowing, you might have basically taken some library which has hidden malware. That all will be basically revealed by static scanning. You should also look for if somehow some sensitive information has gotten embedded into your images. So sensitive information could be your credentials, including your developer credentials, source code. If you're using Git or something, your Git repo, local Git repo might get embedded when you are checking in your source code, and that might land up into the image. And static scanning would basically warn you about that. And then static scanning can look at your configuration part as well. It would basically check if you're using root user within container, which is a bad practice. So basically, both the file system bundle as well as config could be scanned. And there are a lot of open source and closed source static scanning tools available for container nowadays that you could use. Then once you are satisfied, you would go and sign your image to make it tamper proof, so that when you take the container image and release it and deploy it in production, and in the production, you can be sure that it's the image that you have built, and it's the image that has not been tampered, or it is not coming from some other unknown source, right? On the dynamic analysis side, you basically can run your container in a sandbox environment, which will help you detect any stealthy malware or crypto miners. So instead, this could be actually detected in static scanning as well. But static scanning basically is mainly signature based or hash based and some heuristics based. And some of the malware could use some obfuscation and hide itself, so it is not caught in static scanning. So dynamic analysis would help you do that. In dynamic analysis, when you run container in sandbox, you will inspect the network traffic. Is it trying to connect to some known CNC servers, you would basically see signs of crypto mining. And then you could basically flag those images before they are shipped, are released, and before they are run in production. Right. With that, let's switch to post-production. So now in pre-production, we have made sure that our ingredients are pure. We are using trusted libraries. We have scanned them for vulnerabilities. We have made sure that our build pipeline is tamper-proof. Final product is also inspected. So we are sure what container that we have produced is safe and ready for production. It doesn't have any known security issues at least, and they are configured securely. Now it's the time to go and run them in production, and let's say what happens in production. So now let's try to correlate this with a real life analogy outside software applications. So let's say we are talking about office premises and what kind of security we would be interested in looking at. First and foremost, we will definitely like to make sure that not anybody and everybody in this world can come into our office. We don't want anybody and everybody have access to our office facilities, to our office data, our office server rooms, and things like that. So for that, there is a peripheral control where only people having proper access, that is our employees, our contractors, our housekeeping staff, and maybe our authorized visitors, those people only will be able to enter the office. And that's why we have typically periphery control where we have access control and access cards. Is that sufficient? So is the access control at a periphery and entrance, is that sufficient? All of us know that's not sufficient, right? So everybody that comes into office, we don't want them to be able to roam around everywhere and anywhere in the office. For example, there is no reason for an accounts person to have access to server rooms, or for that matter, for an IT team to have access to salary data and payroll. Right? At the same time, we don't need to have payroll employees to have access to our sales pipeline and sales data, and so on. So basically, we want to within office premises also, we want to control the access, who can access what, who can go where. Right? And that's in application terms, that is called east-west security, whereas the peripheral control is called north-south security access, right? So we are going to cover this in context of real software applications. Okay, so how does application production setup look like? So, and this is what Ramesh had covered extensively in his talk yesterday. I'm going to just recap. So production environment consists of obviously your workloads, that is your applications which are running as containers, or in Kubernetes terms, they're called pods. So these workloads would be running on the nodes in your production cluster. So nodes are typical server machines. They could be physical machines, but nowadays they will be all virtual machines in your environment. It could be on-prem environment, or it could be public cloud, private cloud. Each of the node would run kubelet, which will connect that node to orchestrator. It will run container runtime so that it could execute containers, and multiple such containers would be running on each of the nodes. Right? So all the containers are spread over various nodes, and each node is hosting multiple containers. All this is managed by orchestrator, which plays a key role in modern applications. So orchestrator is the one. So if you want to deploy any application in your production setup, you will go and talk to orchestrator and tell the orchestrator, okay, this is my application, please run in run this in the cluster. And you will tell which containers that application consists of. Orchestrator will actually distribute your workload or your application across the nodes. It will pick the nodes and then it will basically distribute the workload. Once the applications are deployed by Orchestrator, it will continue to monitor those for health and uptime and failures, and it will manage auto scale and failover. And these applications need to talk to each other, right? So basically we said, okay, HR basically should have access to employee data and sales guys should have access to customer data. But at point of times, departments or services need to talk to each other. Here, for example, your web application layer might need to talk to caching layer or data layer. So you need to provide service to service routing, and that is what is done by the networking layer. So now we are going to dive into security of each of those components. I'll skip this. This is a little bit detailed view of the cluster in production. Let's dive directly into security, runtime security, which is a production time security. And let's start with workloads. So what's the aim here? So when we are talking about workload security, what is that we are trying to achieve here? So we want to make sure that our nodes and our neighboring containers on the nodes are protected from potentially rogue or compromised containers or compromised workloads. So by compromised or rogue workloads, we mean, okay, the workloads are containers which may have some malware. Though we have scanned images before deploying, we cannot rule out possibility of some malware or some cryptomine or something malicious getting sneaked into it in a stealthy mode. Or it could be that otherwise it was safe container, but because of some vulnerability, it got compromised. For example, once again, we can talk about Log4j. If our containers had Log4j and they were using Log4j, then they could get potentially compromised by remote code execution, right? So, and then the container might turn out to be rogue because the attacker has control over that container. So even with this possibility that our containers could potentially turn into rogue or could get compromised, how do we basically make sure that the damage is limited, which is in application security terms called reducing the blast surface or blast radius. Here, excuse me, guys. Yeah, so sorry about that. The risk here is because on the node, multiple containers from different applications are running on a shared kernel. So if somehow the container security boundary is breached, then the container would have full access to the node and the kernel, and it could basically completely gain control of the node and neighboring containers, right? So, or it could basically consume all the resources on the node so that the neighboring containers basically are starved. So for that, container technology itself provides some features, which were basically mainly packaging related features, but they provide good security isolation. So one is a pivot root, which is similar to chroot, where each container has its own private isolated file system. From within container sees its own file system. It doesn't have access to the host file system, or it doesn't have access to neighboring container file system. So it cannot basically access any file from the node or neighboring container. Namespaces provide isolation in terms of other identities. For example, process. So within container sees processes which are specific to that container. It doesn't see the processes from the node level. It cannot see processes from the neighboring containers, and it cannot then access them, right? On the node, if you go on the node, you will see all the processes, including the processes of the containers. But from within container, you will only see the processes which are running within container. And then C groups, which are control groups, allow rationing of resource utilization by the containers. So C groups limit how much CPU one container can use, how much memory it can use, how much disk IO it can use, so that even if the container goes rogue, it cannot cause the other containers to be starved. Resource consumption in worst case is capped by the limits through control groups. These are the basic security, but it is recommended to use the additional security measures that you have for node security, which basically include don't run container as a root user, don't run in privilege mode. Privilege mode allows container to start another containers because it can talk to host. It gets full access to host. So it's not a best practice to run containers as privileged containers. We talked about pivot root and private isolated file systems, but container technology allows you to mount some of the host or node file system into container. And sometimes it is required for certain functionality, but you should restrict the host mounts. You should never, for example, mount host root file system into container, because it will then give the container full access to the node, and container could manipulate anything on the host file system. It is good or best practice, recommended practice to mount or not mount, to use the host private file system, which is root file system, as read-only. It will make sure that container at runtime cannot download and install any malicious software, even if it goes rogue. Apart from pivot root namespaces, you could fine tune the kind of access container gets to the kernel by using seccomp or SELinux or AppArmor. Seccomp is based on Linux capabilities, which control which syscalls the container can basically make into the kernel. Some of the sensitive syscalls or security related security sensitive syscalls you could block using seccomp. SELinux and AppArmor are LSMs with Linux security modules, which allow you to provide different aspects of access for each of the containers. And depending on what your container functionality is, you should use appropriate security config to restrict the access. And you should always run container with no new privileges, where later on also container cannot gain more privileges than what it started with. If you're looking for even additional controls, because see here, containers are still running on same shared kernel, and any container escape could basically pose a risk. If you are concerned about that and you want to be extra cautious, you could run container in sandboxes like gvisor or Kata containers, where each container is run in separate sandbox, and then the shared kernel aspect is taken care of. Right? I think we are sort of coming close to our time. I'll try to quickly cover rest of the aspects. So like you looked at the security of the workloads, you want to make sure that your infra is secure. So infra consists of your nodes and orchestrator. So at node level, you would do typical hardening of the operating system. Luckily or fortunately for for running containers, there are specific OSs like container OS or core OS, which basically are stripped down a harder version, only contain bare minimum whatever is required to run containers securely. You should use those. You should scan your nodes for vulnerabilities, patch them regularly, make sure that kubelet, container runtime, all up to date and configured very securely. You should not basically allow direct network access to nodes except for your operations people for maintenance. Nobody should have direct network access to nodes. On the orchestrator level, first and foremost, you want to make sure that your orchestrator components are have proper access restrictions. You don't want your orchestrator API to be accessible on internet. And this happened. So in case of Tesla, one of their container runtime, the orchestrator API was exposed to internet, had public access, and attackers exploited that to run crypto miners in that cluster. Then you want to make sure that you keep on patching and updating your Kubernetes version regularly. Admission control is a great sort of security feature or apparatus that Kubernetes provides. With admission control, you can configure policies which dictate what kind of workloads can run in your cluster and what kind of workloads will be rejected. So you can say, okay, run only containers which are coming from trusted image registry, which are signed, run only trusted workloads which have been securely configured. So for example, you can write a policy, don't run any container which is basically running as root, or you could say don't run any container which is trying to run in privilege mode. So what happens here is that though you're actually trying to make sure that you are configuring your containers securely, developing your containers securely, even if some bad container or bad pod gets sneaked into somehow, your admission control policy will make sure that such bad or badly configured, insecurely configured workloads do not run in your cluster. For controlling the access within entities and what entities can do with orchestrator, what your services can do with orchestrator, what your services can access, you should always, or it is recommended to use RBAC, which is role-based access control. Previously, there was concept of attribute-based access control, which has been sort of phased out. So role-based access control is better, which allows you to dictate policy in terms of which service can access what. If you're going to run your cluster for multi-tenancy, where different payloads from different departments or different business units are going to run together, you can use Kubernetes namespaces to isolate them. It provides a soft isolation. It's not like perfectly secure isolation, but you could basically say, okay, my HR applications would run in this namespace in Kubernetes, and my IT applications would run in other. Now let's quickly go over network. So network here is different from the node-to-node networking, which is the basic networking. Here we are talking about application-to-application or service-to-service networking. So networking layer in Kubernetes and orchestrator provide this service-to-service routing, and with CNI plugins or service meshes, you could configure security policies which strictly control which service can talk to which service, right? Network here is, in terms of service to service, is very fluid because your containers are coming up and they're going down. They are basically getting distributed and redeployed and moving around nodes. So your CNI plugins and service meshes keeps track of which service is running where and change the routing at the same point of time, maintain the access restriction policies across various services or various microservices, various containers. So so identity and access here is, we have to think in terms of not user IDs or network IPN ports. We have to think in terms of service identities and which service can do what, which service can access which resource, and which service can talk to which other service. Monitoring and auditing is important because we are running tens and thousands of containers. They are moving around the nodes, and services are coming up and down. So to be able to secure them, you need to have visibility, which is where you need to basically know which workloads are running, what they are doing, which service is talking to what, so that you can basically monitor them. And you could basically, if something goes wrong, you could detect anomalies and drifts, and you can take corrective actions. Okay, now this brings us to where can we get more data, and these are the sources. You could go to MITRE site. Kubernetes security details are available in Kubernetes security pages, and CSI benchmarks gives you best practices for securing your Kubernetes and Docker containers. So that with that, I would like to close the talk, and I'll be basically thanks for joining and being patient here. Thank you. And if there is time, I'd be happy to take questions. Thank you.
Thank you so much, Mr. Ajit. We have one question for
Sure.
you. How can role-based access control be achieved?
Yeah, so role-based access control first starts with a little bit of a philosophy. You have to think of designing roles in your system. The roles basically means resources and action. So role says, okay, can somebody do this action on this particular resource? So it could be database. So can reading a database, read access to database is one role. So you could basically have these granular roles where you basically define various actions that could be done on various resources. And then you map them to the services, right? So basically, okay, does HR service has access to read this particular database? And that matching or mapping in Kubernetes terms is done using role binding. So you have roles which say which resources and which actions. On the other side, you have service accounts which says which entities. And then role binding basically is the one which basically binds the service accounts to these roles. And that is how you achieve RBAC. I hope that answers the question.
All right. I believe we have no more questions. So thank you so much again, Mr. Ajit, for this engaging and informative talk. I particularly like the way you used real-life analogies to explain a couple of complex concepts that you showed in today's talk. So thanks again so much for joining us today and giving us your valuable time.
Thank you.
Thank you.